So, hello and welcome to today's Vision Channel session, where we want to answer the question how to create 3D camera data with true color information, because in 3D vision applications, it is often not only the shape, position, and orientation of objects that play a role, but also color information is often crucial. One example of this could be a robot vision task with a sorting function for differently colored parts, like these here. We have printed some parts here that we see later in the lecture of my colleague. In such cases, depth information must be combined with the real colors of the scene. And today I have invited my colleague Ute Seitz in her role as an application engineer to show us how to superimpose the color information of a 2D RGB camera with the position and the depth values of a stereo vision camera and make it usable for 3D applications, for example, in robotics. So then, I would like to ask Ute, are you ready? And are you here?
I'm ready and I'm here.
Then, I would say the stage is yours. You can share your screen and have fun, yeah.
Before I start explaining how to add color to the 3D data of your Ensenso camera, I will have a quick look at possible representation of 3D data. So as an example, I will talk about 3 representations, and one is the point cloud, a 3D mesh, and a point map. So the point cloud is the very basic representation. You have points that are represented within a coordinate system. So this is displayed here. You see the 3 lines. Each point is represented by its X, Y, and Z value. And depending on the data container, you can also add some attributes, for example, like color, as you see here. And in point clouds, you can compute stuff like a bounding box that fits around all the points. Then you have an idea about the dimensions of the point cloud. Or you can compute, you can fit geometric primitives into the points. So you can fit a plane into the points or several planes and compute intersections. So these are the basic operations you would do in a point cloud. The next is the 3D mesh, and this is generated by computing small triangles of 3 neighboring points, and that way you get a surface model. The surface model may be the most known file formats are PLY or STL files, and they are commonly used, for example, for 3D printers, or if you want to search in your point cloud for a specific 3D model, for example, when you're doing bin picking, then you can create your own 3D model by saving it as your 3D data as a PLY file and use this later on to search for it in a point cloud. And as you see here, the triangles also might be assigned with color or depending on the data container, on different attributes. And then we come to mapped 3D data. This is the most challenging to understand. The first are quite straightforward. And the mapping is you represent the 3D data depending on or based on the camera images that provide the raw material for computing your 3D data. So here, as an example, I showed the image of an Ensenso camera. So if you, for example, use a C series, it has a left and a right eye. And the left is the reference image. This is this one. And the 3D data is mapped to the pixel coordinates of that image. So to pick coordinates for a specific area of that you see in the image, you just use the pixel coordinates. For example, if you want to have the 3D data of that object, you would use image processing algorithms to segment that region. And the region consists of the pixel coordinates here. And then you use that pixel coordinates and go to the point map. And the point map is a 3-channel image consisting of an X, Y, and Z channel. And then you go to the X channel, use the region coordinates and pick the X values. And then you go to the Y channel and pick the Y coordinates, and same for the Z. And the advantage of that mapped data is that you can use the image that you have anyway from the camera sensor to segment regions of objects that you're interested in. And you can, for example, use the Z image to apply a simple 2D image operation like a threshold, and you can easily remove a background, for example, by just thresholding over the Z values, and that way you can define the region that you are interested in. And this is much faster operation than computing stuff within 3D data like a point cloud. Now we come to the color. And yeah, what you basically have is a color image. So you have your 3D sensor and you have a 2D camera, and from the 2D camera you get a color image. And to combine the 3D data with the data in the color image, the data has to be remapped from that what we looked at before. So now the 3D data has to be sorted to match to the pixel coordinates of that image. And because it's from a different camera sensor, the pixel position of that object would be other pixel coordinates than we had in the left Ensenso camera image. You also get a 3-channel image providing X, Y, and Z data. And this is not the point map, but it's called a render point map because the data is rendered to the view of the color camera. And then you can, the same way, you can use image processing algorithms to segment whatever you want using color information or whatever, obtain pixel coordinates of your regions of interest, and then use that pixel coordinates to pick the X, Y, and Z data from the render point map. One thing you have to do in advance, you have to tell the software the relative orientation from the left Ensenso camera coordinate system and the color camera's coordinate system, because the 3D data is represented as the color camera would see it, and so you have to apply those transformations. Now I show you how you could save 3D data with color. The easiest way is to save the PLY file. And if you, I did it here with a FileCamera. I saved the data from the 2D and from the 3D camera, and I just used an Ensenso C. So I saved that and that data from those cameras and created a FileCamera, as you see here. And if you open this in NxView, NxView will display in the 3D view the colored point cloud. And using File, save 3D mesh. You get a PLY file, and you can open it, for example, this is CloudCompare. This is an open source tool that you can download and use it. So I've prepared this to show you how it would look like. So if you select open and choose your PLY file, and then you get such a checkbox here, you can go just to apply. Wait a moment, and then you have here 3D data with color. And if I zoom in, then we see this is the 3D mesh. You see here, yeah, it's a surface. It's not only points, but you also can visualize the points. In CloudCompare, they are called vertices, or in PLY file, they are called vertices. So you enable them and you make the mesh invisible, and then you have colored points. So this is the easiest way to save colored 3D data from your Ensenso camera. You just save the 3D mesh as a PLY file. And how to work with the mapping, with the mapped 3D data, I prepared some stuff in an application. So this is done using Helken, just because Helken is easily produces windows that shows images, and you can do it with any other. You can write a program in C++ or C or Python, opening some windows to display your data. So this is just the point cloud. So you see these are only points. And now I have split the point map. So the point map is that 3-channel image that is mapped to the left camera image to get the X, Y, and Z image. And this is the left Ensenso's camera image. And what I want to show you here is, if you look at this position, now you see only zeros. But when I'm back with my mouse on the images, you can see the pixel coordinates in the image where I'm hovering my mouse over. So for example, I go to that point. So I have something 1100 and 1200 here. And if I go to the Z image at the same position, you see it's the same value. And here it's the same, and here. So this is just to show you that you can use some algorithms to get pixel coordinates from that image and apply them in the other 3 channels, whatever you want to use, to get the coordinates that are stored in the images. So the X coordinate is just stored as a gray value in that image. So here we have an X value of -30, a Y coordinate of 137, and a Z coordinate here of -28. And now I computed the rendering. So I told the software, use the viewing point of the color camera and compute or rearrange the 3D data as it would look like in the color image. And the same here. If I go to that point, I have different values. You see it's not 1100 and 1200, it's 600 and 900. Same here, here, and here. And you can do the same thing. You can just, for example, look for edges in the image to find the area of the box, and then use the pixel coordinates of those edges to get the corresponding 3D data out of that 3 images. So what you actually do is you calibrate the color camera to the Ensenso camera. You capture an image pair with the stereo camera and with the color camera. You compute the disparity map. You rectify the color image, and this just means you remove the distortions. And this is just, the coordinates are computed as the objects look in real life, and there are no distortions. So you have to remove the distortions from the color image, that you have straight lines and not some bended shapes. Then you compute the render point map. This is the 3-channel image mapped to the color image. And then you just save the rectified color image and you save the render point map. And then you can combine 3D data and color image using the pixel coordinates of each. And that's the binding element between the color and the 3D data. The benefits of mapped 3D data is that the color image may also be used for AI-based segmentation. So you have more ways to find areas that you want to use for getting 3D data. And 2D operations are usually faster than operations in the point cloud. And the mapping provides additional information like where the pixels come from and which are neighboring. So in the mapped 3D data, the point cloud is implicitly included because each pixel contains an X, a Y, and a Z value. So using the information from one pixel coordinate over the 3 channels provides you one point in 3D. And thus you can compute the point cloud from the mapped image. And if you want, you can still use an operation to compute a 3D mesh to have the surface model that you can use as an PLY or STL file later. So this was the basics for combining 2D and 3D data. And thank you for listening.